Hello guys, so today we're going to be integrating e to the negative x squared going from negative infinity to infinity dx, which is, well, I said it's equal to I, for well convenience purposes. And you'll see why in just a second. So this is known as the Gaussian integral. It's usually used in normal distribution and statistics in general. Sometimes you may see it in physics as well. But other than that, there are a lot of applications of this integral in real life. So the method we're going to be using to evaluate this integral is known as, well, polar coordinates. So we're going to be using the method of polar coordinates here. So to do that, let's notice the fact that if you change this x to y, you still end up with the same integral. So if I say e to the negative y squared dy, this is still I. So if I multiply these two, I end up with a double integral with the same bounds, and using properties of exponents, we can just add these guys up. So let's go ahead and do that. So negative infinity e to the negative x squared plus y squared dx dy. So this is what we end up with, and also this is equal to I squared, which is going to be important in the end, but for now let's forget about that. So now let's do the standard Cartesian coordinates to polar coordinates conversion, which is just going to be x is equal to r cosine of theta and y is equal to r sine of theta. So x squared plus y squared will equal r squared cosine squared theta. I'm going to just factor out the r squared here to make things much easier, plus r squared sine squared theta, but again, I factored out the r squared, so just sine squared theta here. And using trigonometric identities, we know that this whole expression is just equal to 1. So we only end up with r squared instead of, well, x squared plus y squared. So if I write this down in terms of polar coordinates, we get, okay, actually the bounds still don't stay the same, but we're going to be converting them later on in this video. E to the negative r squared, something as the differential, some dr d theta of course, but what next? What is next to dr d theta here? So to figure that out, we're going to have to use the Jacobian determinant. I won't be going into too much detail about what the Jacobian determinant is. I'll be making a video on that though. But the Jacobian determinant is basically, the simplified version of it is that it's the scale factor that is used to, well, do a double substitution. So since we're changing dx and dy at the same time, we're going to be changing two variables at the same time. So we need the Jacobian determinant here. And the Jacobian determinant is denoted in this way or in this way. They're both the same thing. So if I open up the Jacobian determinant, it basically, well, in this context, it basically means the partial derivative of x with respect to r, and underneath the row, in the same column, it's going to be the partial derivative of y with respect to r. And for the next row, column, it's going to be the partial derivative of x with respect to theta, and vice versa for y. All right. So let's just go ahead and plug our x and, well, y values here, which are these, and find the Jacobian determinant. Now, it might look pretty nasty, but there's going to be a pretty good value that comes out from this determinant, I promise. So, if we write r cosine theta instead of x here, and take the partial derivative of that with respect to r, cosine theta is just a constant. So we can just factor that out, and the derivative of r with respect to r is just 1, so and times the constant, of course. So we end up with the determinants of cosine theta in the first row, first column. And for y here, we know that it's r sine theta. So if we take the derivative, the partial derivative of r sine theta with respect to r, we end up with sine theta. Same procedure as the one before. And for x here, if we take the partial derivative of that with respect to theta, so r is a constant this time, we end up with negative r sine theta. So negative r sine theta. And for y here, we have r sine theta. If we take the derivative of r sine theta with respect to theta, r is again a constant. So the derivative of sine theta with respect to theta is just cosine theta. So we end up with r cosine of theta. And we're going to be doing the standard procedure for computing a determinant of a 2 by 2 matrix. So multiply these guys and multiply these guys, but there's a negative here because we're subtracting these two. And also timesing it again with a negative. So r cosine of theta, cosine squared of theta, minus r sine squared theta. So if I times this minus by minus, we get positive, so let's just get rid of that. And if I factor out the r here, we end up with cosine squared theta plus sine squared theta, which is just 1. So it's just going to be 1. All this work for just to get r. So if we go back to the integral here, we can say that well, we didn't determine the bounds yet. We're going to do that right now. So the indefinite integral of e to the negative r squared is r dr d theta in this case. So for the bounds, we can say that since radius will never be negative, it's just going to be r is equal to 0 and r is equal to infinity for the lower and upper bounds. This is for the first integral. Now if we get to the second integral, it's going to be a little more complicated. The minimum angle is going to be 0 and the maximum angle is going to be 2 pi. But why is it 2 pi? You might be asking, since if we draw the graph of e to the negative x squared, from negative infinity to infinity, it clearly ends at pi, right? The maximum angle. Well, yeah, you're right, but this is not what we're looking for. Since we have a double integral, which is known as a volume integral, we're evaluating this using 3D coordinates. So we still have this shape, but we're determining the area of these circles. Like if I draw this somewhere around here, we still have the same shape as before, but we're going to be finding the area of these smaller circles here. And to do that, if you look at the graph from a bird's eye point of view, you'll notice that it's just going to be a circle, a big circle. So that means its minimum angle is 0 and 2 pi. And now if we get back to computing this integral, it's pretty straightforward because as you can see, there's a u substitution you can do with the r squared and r here. So u is just going to be r squared du over 2 is r dr. Since the derivative of r squared is 2r, I just halve both sides because 2 is a constant. So if we factor out the 2, 1 over 2, we just get a 1 over 2 on this side. So 1 over 2 is on here. And also we can evaluate this integral here. because there's no theta term. And this evaluates to, well, 2 pi. Because if you integrate 1 with respect to theta, you just get theta. And input the bounds, 2 pi. So 2 pi. And these, of course, cancel out. Now, if we go back to the other integral, we have the integral going from 0 to infinity. These bounds are still the same for u, by the way, because if you square 0, well, you get 0, square infinity, still infinity. And this is e to the negative u du to negative u du. And if you integrate this, you end up with negative e to the negative u going from infinity to 0. And don't forget about the pi here. So if you put the infinity instead of the u here, you just end up with 0. So let's go ahead and write that down. And negative times negative is positive because we're going to substitute the 0 in. So positive e to the negative 0 is just, well, e to the 0, so that's 1. And we end up with 1 here. So 1 times pi is, well, pi. So basically, I squared is pi. So we were trying to find I in the first case. So I is going to be root pi. All this work for such a nice answer. And as a bonus, since we know that e to the negative x squared is an even function, we can say that the integral going from infinity to 0 to infinity of e to the negative x squared dx is going to be square root of pi divided by 2. Thank you for watching.